All right, let's go ahead and work through a problem here and see whether we can use the steps of statistical investigation to figure out whether dyslexia is a more common thing than the recorded diagnoses would indicate. Okay, so I'm going to start by ignoring all the formulas up there because I made this for a practice for students in my in-person class last year. You guys don't really have to worry about formula memorization, and so we'll just ignore that part. All right, so we are interested in testing a sample of the adult population. Okay. To see if there is evidence that the rate of dyslexia is higher than 5%. So, all right. So, our null hypothesis is actually going to be the opposite of this, right? So we're going to test that pi is equal to 5%, or you could write pi less than or equal to 5%. Either one is fine. The alternative hypothesis is pi is greater than 5%. All right, because this is what we want to be able to conclude at the end, right? And so that's what we're hoping to see evidence of. Okay, so we randomly sample 250 adults. Okay, so this is N, and find that 23 likely have dyslexia. Okay, so our p hat is 23 over 250. All right. So the validity conditions for a one proportion theory-based hypothesis test is that we have N of at least 20, right? And 10 successes, 10 failures. Okay, so we have N of 250, we're fine. We have 23 successes, right, people with dyslexia, and 222, I guess. No, 227 people that don't have dyslexia. So we're good. All right, now we have to calculate the population standard deviation, right? And to do that, I'm gonna just peek up here and we see that that's pi times 1 minus pi over n. We've looked at, right? So pi is 5%, so square root of 0.05 times 0.95 over n is 250. Okay? So if I type that into my handy calculator, I would get 0.0138. All right. Now, we need to calculate the standardized statistic, z. Okay? So the statistic minus the mean of the null distribution So 23 over 250 minus 0.05 divided by 0.0138 is what we'd have for our standardized statistic. And okay, so 23 over 250 is 0.092. 0.092 minus 0.05 over 0.0138 is 3.0435. Okay. All right. So we've got pretty decent evidence, right, that the prevalence of dyslexia in the adult population is not 0.5, right? So the way I'm thinking about this is, here's my normal distribution, 0, 1, 2, 3 standard deviations, right? So we're somewhere way out here, and we have a pretty small p-value corresponding to the area under that curve. All right, so we're now supposed to use the theory-based inference applet to get the p-value for that test. All right, so we go to the theory-based inference applet, and we type in Rn. We type in the count, which is 23, and that gives us a sample p-value, right? And we would like a test of significance. Okay, so we are testing pi greater than 0.05. All right, so we get our standardized statistic is 3.05. That's good. It's always nice when what we got more or less matches what we calculated manually. And our p-value is 0.0012. Okay. So if I switch back over here, P equals 0.0012. Okay, and as expected, it's on the same side as the picture we drew, and it's about as small as we thought it would be. All right, so the conclusion is that with z equals 3.0435, we have strong evidence to reject H naught that pi is equal to 0.05. It is more plausible that pi is greater than 0.05 because under H naught, the probability we observe 23 out of 250 people with dyslexia is 0.0012, which is not, oops, very likely. It is much more likely that HO is not correct. Okay, so that's the overly thorough explanation of the conclusion. You can probably get away with the first two sentences there, or anything from here to here, right? But I decided to be a little bit more detailed for the purposes of explaining this whole problem. Okay. You conduct a second sample of 120 adults, and this time you find that 14 individuals have dyslexia. Okay? And the first question is, does this second sample contradict the results of your first sample? Okay? Why or why not? And the answer is, it's a random sample, right? So we got different people than we did in the first study. So no, this doesn't contradict anything. This is just another random sample. And different samples produce different results. No big deal. Just another day in statistics. Okay, our sample proportion is 14, right? Successes out of 120 failures, which is 0.1167. Okay. Our population standard deviation, using the one proportion applet, so is, so we're gonna do 0.05. Sample size is 120, right? And let's go ahead and draw 1,000 samples and not animate anything, okay? And we're gonna look at, let's do number of successes. All right, draw samples. Okay, so we can do summary stats, and let's switch to proportion of successes so that our summary stats make sense. Okay, so our population standard deviation from the applet, right, is 0.019. But we could also use the population standard deviation that we calculated before, which is 0.0138. And that's fine. Those are not, super different. We will be just fine. Okay, so standardized statistic, 0.1167 minus 0.05, right? Divided by 0.019. We'll just use the applet version this time. All right. So we've got our standard statistic as get a standardized statistic of 3.511. Okay. So we go back to our applet, and we type in, so let's type in as extreme as, and this is where we put our proportion of successes in, 0.1167. Count. Okay, so we have a p-value of 3 over 1,000, right? Okay, 3 over 1,000 equals 0.0030. Okay. Now, using the histogram below, draw lines indicating the cutoffs for extreme values. Okay, so we have 14. Okay, so this is 15. This is 14. Okay, so right, and anything in this direction is more extreme than what we observed. Okay, so if we saw 14 people out of 120 or 15 people out of 120, those are more extreme. Okay, so this is what's going into our p-value calculation. Okay, the standardized statistic is 3.5, which corresponds to quite a lot of evidence, right? Okay, very strong evidence against the null hypothesis. So we reject HO and conclude pi is greater than 0.05. Okay, and technically that's the answer to the next question. All right. Now, on to the hypothesis practice portion of this review sheet. A number of problems that feature Edison the puppy. So you are to identify the parameter, define success, write the null and alternative hypothesis, calculate the sample statistic. And then can you use theory-based inference? Okay, so parameter for the first problem. Edison is a very talented Jack Russell Terrier puppy who is competing to be in a demonstration at the Puppy Bowl. To qualify, Edison must catch more than 75% of the frisbees thrown for him over the long run. Okay, so parameter is pi, long run, proportion of frisbees caught. Okay. Success equals frisbee catch. Okay. The null hypothesis is pi is less than or equal to 0.75. The alternative is pi is greater than 0.75. And the sample statistic is p hat equals 16 out of 20 equals 0.8. All right. Then, could you use theory-based inference on this study? We have n of 20, but we have 16 successes and 4 failures, so no theory-based inference. Because we don't have enough failures. Okay? All right. Edison has been watching squirrels and would like to know if, when being chased, squirrels turn right and left equally often, so that he can catch them more easily when he escapes. He monitors the squirrels that come into his yard for a week. He notes that in 30 observations, squirrels turn left 20 times and right 10 times. Okay, so parameter, pi equals proportion, long run proportion of times squirrels turn right. Okay, success equals squirrel turns right. Okay. Sample, okay, null hypothesis, pi equals 0.5. HA is pi is not equal to 0.5, right? Because he doesn't care if they turn left or if they turn left more or less than they turn right. He wants to know if they turn left or right equally often, okay? So p hat equals 10 over 30 equals 0.333, and we can use theory-based inference because we have at least 10 successes and 10 failures. All right. Edison might also be called destroyer of toys. His owner would like to know whether, in the long run, he destroys the squeakers in more than 65% of the toys she buys for him. Over the course of a year, she carefully records the fate of each toy, finding that of the 24 squeaky toys she bought, only 8 still make noise. Alright, so pi equals long run proportion of squeaky toys destroyed. Okay, success equals squeaky destroyed. HO pi is less than or equal to 0.65. HA is pi is greater than 0.65. P hat is, so 16 out of 24, the way we've defined this, right? Which is 2/3, so 0.6667. All right, we have 8 failures, so we do not have enough failures for theory-based inference. All right, Edison is perfecting his puppy dog eyes. He has practiced very hard for the past month and would like to know if giving his people the look results in treats more than 50% of the time. Over the course of 2 weeks, Edison uses the look 56 times and gets a total of 30 treats because Edison is a spoiled puppy. All right, so pi equals long run proportion of treats after the look. Okay. Success is getting a treat. HO is pi equals 0.5. HA is pi is greater than 0.5. P hat is 30 over 56. 0.5357. And we have 30 successes, 26 failures, and n is greater than 20, so yes, can use theory-based inference. Okay, Edison has staring contests with the cat next door, who he has named Satan. He would like to know whether he has an even chance of winning the staring contest with Satan over the long run. He is a statistically inclined dog, since he lives with me, and he collects data over the course of 2 months, finding that of 184 staring contests, he won 80 times. Okay, so pi is the long run proportion of staring contest one. Success is Eddie wins the staring contest. HO is pi equals 0.5. HA is, so if he has an even chance of winning, so that's going to be pi equals not 0.5. Okay, so even chance, we care about whether it is equal to 0.5, so the alternative is it's not. All right, p hat equals 80 over 184. Equals 0.4348. All right, and since n is greater than 20 and success equals 80, failure equals 104, theory-based inference is fine. All right, so that concludes the Chapter P and Chapter 1 review sheet. And I hope that seeing those problems worked out has helped.